So I guess this was like a switch gear to something not the very different thing. So my talk will very much based on the mathematical setting because I haven't do very much the HPC stuff. But actually, I have implemented with MPI, so just a very like a very broad review of this implementation on the HPC. But what I will do is focusing on some technical issue that we need to focus on when we implement such techniques into computing the wave propagations. So this is like a technology that has been widely used in like fluid dynamic computation. So what I will discuss not only here about this seismic wave, also for this coupling with multiphysics. What we'll introduce here is maybe some stiffness terms. If you heard about this stiffness terms, that means, okay, you will need very fine time stepping if you are using explicit time stepping. So that will be a very important issue in implementing HPC and also for simulations as well. So what I'm going to talk about, first of all, is the questions we are like in implementations we would like to focus on. Of course, the conventional like waveform inversion and the seismic modeling, and on elastic problems, and of course acoustic. And for oceans, we have a coupling acoustic elastic. And for the more implementations, we also consider the reservoir simulations, such as the fractures. We have like coupling multi-phase interacting, such as polar elasticity, and this kind of things. So, so for this inverse problems, we need to have a very efficient computation for forward modeling so that we can actually compute this gradient. And that is the major consider of how we develop this new algorithm. We want to compute it efficiently. We want to compute it very stable with like tolerable time stepping as well. So let's go into this, this method. Before that, actually, we somehow, if you heard about this discriminatory method, you will know some beauty of this method. One is that it can use any kind of elements. For example, like the most easy, like this one is the unstructured tetrahedral or unstructured triangle, which can be very well implemented to be a body-fitting mesh, which means we can locally refine the mesh to fit the very complex geometries. And this is the kind of comparison using finite differencing using unstructured mesh. And you can see this by using relatively same degree of freedom, we will absolutely prefer this figure, right? It's a kind of a more like an elegant description of the model. So also for the three-dimensional, you can actually expect a better approximation of the geometry of the model by using unstructured tetrahedral mesh. So by doing that, actually we need to develop a very very elegant meshing technique to really build the model. This is a technique of so-called moving mesh we actually developed for this for implementing with this DG method. And the idea is we want to just control this mesh with this quality, which means we don't want to have elements that will be extremely thin and that will greatly affect the CFL condition. So what we develop here is we use optimization methods by like formulating objective function based on this distance measure between meshes. And the conventional one is that non-continuous, non-smooth objective function, but we actually smooth it by approximating that. and developing a like joint inversion of this body mesh as well as the surface mesh, so that we can actually also change this topology as well. So this is a technique that we can use for the building the model as well as for full waveform inversion. If you are interested in that, we will have a poster this afternoon about this implementation in full waveform inversion. So, so let's discuss some of these DG methods we developed here. I mean, there's a lot of DG methods are available, and most of that general DG method will provide the polynomial order of accuracy, which means we can get very accurate results for the wave field. And also, it can be implemented with ancestral mesh as well. And it's the most important like idea of DG is to use the discontinuous solution to approximate continuous solutions. So that actually, when you use DG to compute a wave field, it actually a discontinuous wave field, but in terms of polynomial approximation, it will approach the true solution as a smooth function. And that is a benefit if your true solution is actually discontinuous, because the nature of this discontinuous function could just characterize this discontinuous true solutions in a very natural way. That will happen when you have fluid solid boundaries or you have a fracture. And that is very common in reservoirs or in this, if you are using like hydraulic fracturing, you can expect it to have an opening over this material. And that is the critical area that we would like to use this discontinuous method to characterize this wave field or interaction with seismicities. And also, this what we develop here is a modified penalty. I mean, the penalty is a very large category. What it does is to like stabilize these algorithms by making this operator to be coercive or to be like well behaving. And what we do here is, especially for the wave equation, we can make this penalty to be adjustable based on problems. So what it means, it doesn't depending on the mesh, or it's just depending on your parameter of seismicity. And more importantly, the penalty coefficients will affect your CFL conditions. So I will show after is that the comparison of this method with upwinding. And that means actually we can adjust our penalty coefficients so that it can actually get a better CFL condition than the upwinding. So I think this is just a very naive implementation with the high performance computers. We just use like up to 1,000 cores for these implementations, and this is stone scaling speed up, but I mean, this is a very naive implementations, and there's a lot we can do to still optimize this code. So a lot of things we can do at this moment in my mind is that we can do this domain decomposition optimizations. We can minimize the connections, and also we can do this like pipelines to make algorithms to be more efficient. And also, because we are implementing checkpointing for these full waveform inversions, we need to optimize this I/O as well. So a lot of we can do to really make this research code to be more like practical implemented. And this is like a numerical example showing how we can accurately deal with the fluid-solid boundaries. Just convergence tests and also this alignment with the phases. So which means we actually catch all the phases that can be generated by this fluid-solid boundary. So this, we come to a very like a critical point we just mentioned is that this numerical flux, I mean, can actually changes your eigenvalues of the operator. And here what I show is this black dots means the central flux, And also the red part is our method, and the blue part is the upwind flux. So for this figure, actually we are using the panel coefficient approximately about 0.5, and you can actually get this distribution of eigenvalues similar to your to the upwinding flux. But actually, for these implementations, we can choose the coefficient of penalty to be smaller, then this area will shrink a little bit to this area. So that means it gives us freedom to choose this penalty flux depending on your your preferred time stepping and depending on your problems. And so another thing is that if you would like to use the central flux, there are some problems. First of all, it's the distribution of eigenvalues on the imaginary axis. That means you can only use if you are using Runge-Kutta, for example, you need to use order higher than 3, the third order Runge-Kutta, to make this algorithm stable, because the explicit Runge-Kutta convergence radius was something like this. And then these eigenvalues were not included in the stable region. So that is some drawback if you're using central flux. And the other is if your operator is slightly non-symmetric. For example, like here we have free solid boundaries. This jump is a little bit unsymmetric. You will generate a positive part of eigenvalue, which means you will not be able to get a convergence, a stable algorithm by using explicit scheme. So what we do by applying the penalties to move this positive part, even if it is the original operator is not symmetric, we can still move this part back to the negative region, so that we actually can implement this with the the explicit Runge-Kutta. And so it's I mean, the explicit scheme is a very standard way to implement with HPC rather than the implicit scheme. But nevertheless, we still need to consider some situations when an implicit scheme needs to be considered, especially the case with stiffness. So the next I will introduce is these problems with the stiffness. And before that, this is an example of also the free solid simulation together with the heterogeneity as well as the anisotropic. So it's just an illustration. And so also for the free solid with complex geometry, we can also give a simulation over this very sim model with ocean layer as well. And so the next is so-called this rupture and fracture problems. So basically this solution of this type of problem will be discontinuous. And the difference, maybe you have always heard about the rupture or the fracture, but actually they are different. The fracture problems actually is easier because the system will be linear. The difference between these two systems is that for the rupture, the normal component and tangential component will be coupled. But for the fracture, they are decoupled. So that means this can end up with a linear system if you are using linear friction law. And that one will always be nonlinear, and even if you are using linear friction law. And the other thing is that this kinetic energy for the rupture problem, it actually can be accumulating because you are actually considering the pre-stress. And for the fractures, it should be always dissipating. So, but what I want to show here is that because we are focusing on this spontaneous rupture, which means we can easily convert it to fracture because we started with the more complex problems, and it will always be easy to convert to the easier problems. And of course, this all discussions is depending on the mathematical discussion on the well-postedness of the system and what this penalty flux is applied and is chosen to ensure that this system is all behaving well. And so most of this discussion is on this most general implementations. So this is like an example on this rupture problems. So basically, it's the relatively difficult one. And the top two, actually, it has a heterogeneity medium. And you can see from the wavefront that this side has a higher velocity, and that side has a lower velocity. And the second one has like a heterogeneity on the geometry, which means the rupture is not a plane. And so you can see there's like a kink over these two intersecting fault plane. And the propagation of wave will generate actually a very significant discontinuity and very significant like a jump, like looks like a singularity over the solutions. That is how this stability issue comes into place. So actually this stability of this nonlinear system is like driven by this like stability of the friction law as well as the like controlled by the numerical flux. So in this case, we need to choose sufficiently large numerical flux to actually make this stable. And the drawback of choosing sufficiently large numerical flux is that we need to sufficiently tiny step if you using the explicit time stepping. So here we actually implemented with the implicit explicit scheme. And the strategy of using implicit scheme is we only use that on this where necessary, that is this rupture plane and its two-dimensional problems, so that we can actually only solve implicit problems on this two-dimensional instead of three-dimensional. So that is, and also this kind of can be used as like a preconditioning method by using iterative coupling method. And so actually, that would be a good way to implement it with HPC. And the next example of how this stiffness come into place is so-called this dynamic permeability, or the pore elasticity problems. So basically, this pore elasticity problem is driven by this Darcy's law, which depending on the frequency. And what we'll end up with in the time domain is this convolution term at each time step, which will generate also this stiffness. And that will, first of all, this system is linear, but actually, nevertheless, it will require a stability result to actually control the accuracy of this scheme. So what we are doing is that we also use this kind of iterative coupling by implementing different time steps for the stiffness part and the non-stiffness part. And the system of motion is like this. So as you can see, it's linear. And on the background is a numerical result in two dimensions. And we can actually see this slow P wave come into being. So as a conclusion, actually, we have a DG method that's developed based on this analysis of the particular physical problems. And what we consider is what can be like implemented with this method. Of course, with the fully elasticity and the coupled fluid solid, and also pore elastic and the nonlinear effects. And so that's a lot of implementations that can be like used with this method, and that can be a relative future work. So we want to make this software open, and that everybody can check whether this one can be well adapted to your problems, as well as can be implemented for performance. So Yeah, so I would like to thank this sponsorship to the Jimmy Group and also for the Simons Foundations. And so keep an eye on our website because our software will be published there. Right, thank you. Yeah.
Sure.
Yes, please.
One of the typical advantages when they compare DG with continuous Galerkin has been that you could use explicit time marching with DG because of the diagonalization of the mass matrix. But now you're saying you're using implicit methods. So have you compared with continuous Galerkin, and do you still have implicit DG? Does it still have any advantage over continuous Galerkin?
You mean this implicit DG have like implementation issue, or what's your particular like question?
Typically, the advantage that has been claimed for DG is that mass matrix diagonalization, so you can continue to use explicit methods which are nice and easy.
That's right, yeah.
Now
So
are you losing that advantage? That's my question.
that's right. So one thing that we want to use the implicit scheme is because of the stability issues. That is not like a very, not inevitable. But actually, what we are using is so-called iterative methods. So that actually you can still use this diagonal, like a block diagonal character of this mass matrix. And that's also one thing that we want to implement it with the high performance computing, because if you are actually using this direct solver to factorize this method, and you will end up with something like very complex algorithms. Or actually, if you are considering very small area, you are using like an implicit method, you can still, for the majority part, you still use the benefits of DG. But for this particular part, you can separately consider it as an implicit, like locally implicit problem. Yeah.
Let's thank our speaker again.
Yeah, thank you.